All right, so now we are going to have a look at the equilibrium solutions that are given by this free energy mathematically. We are not going to do the complete treatment as we did for the continuous phase transition, simply because it becomes a little bit much work for too little benefit. Also because we have grown confident in our ability to understand things graphically, and I would like to reason in that way so that we see that we can actually go quite far computing a relatively small number of things. All right, so at equilibrium, the first derivative of the free energy with respect to the polarization has to be zero. I have written here, by the way, the free energy we are going to use, in which we have already justified, and we are going to, for the time being, assume that T0 is positive. And I have removed T star. T star, we will talk about T star right at the end. Okay. So we need this first derivative of f with respect to p to be 0, and that means that we have something like this: p alpha prime gamma equal to 0. And we are, of course, always working at 0 applied electric field. The electric field would be here as an additional term, but it's not important for this discussion. Well, okay, so this is our equation of state for this case, in which we have a theory for a discontinuous phase transition. It's slightly more complicated than the previous one that we saw. Essentially, we have this extra term. But we can already see immediately, I took already common factor, the polarization, that in principle it has certainly one solution that always exists, which is p equal to 0. So this is always a solution. We don't know, in some temperatures it will be a maximum, in some other temperatures it could be a minimum. When will this be a minimum, so therefore a stable solution? Where that one is very simple, because the curvature of the free energy around p equal to 0 is directly given by alpha. Okay, so this solution is a minimum for temperatures above T0. Well, it always exists and is a minimum. Let me write it explicitly. Okay, we could figure it out by evaluating the stiffness, but again, it's the second derivative of f with respect to p, evaluated at p equals 0, so it's given by that, which graphically we already knew, right? If this alpha is positive, it's a minimum. That's it. There isn't really anything else to it. All right. The other solutions are going to come from finding the values of the polarization, where this parenthesis here, this expression, is 0, right? And so here, if we take p squared as our variable, then we know the analytical solution for that is something like this. You know that p squared has to be minus beta plus minus beta squared minus 4 times gamma alpha prime t minus tc, square root of that, divided by 2 times gamma. Slightly more complicated, not very complicated, but as compared to what we had before, certainly more complicated. All right, so now we have to really worry about the conditions for existence of this solution before we worry about it being a maximum or them being maxima or minima. What do we have here? We have here a squared, polarization squared, so this whole thing on the right hand side has to be a positive number, otherwise solutions don't exist. But also we have here a square root, so on top of that or before that if you want, what we have inside the square root also has to be a square number, sorry, a positive number, right? So let's start with that. So let me call what we have in the square root of delta square. So let me, for gamma alpha prime, t of this should be a 0 minus t0. This thing here has to be positive in order to have solutions at all beyond p equals 0. All right, when is this positive? When we can solve for the temperature, essentially, right? So what can we do? We can move this term over there, then we can divide by this prefactor, and we can move t0 back, and then the temperature goes to the pointy part of the inequality, so the temperature has to be smaller than t0 plus beta square for gamma alpha prime. I think I did. All right, sounds good. So for temperatures below this number, we have solutions. If T0 is positive, which we are assuming tentatively, if T0 is positive, here we are adding to it a positive number, beta square is positive, gamma and alpha prime are positive. So there, if T0 is positive, we always have solutions, apart from this one, okay? If T0 is negative, then having solutions requires this addition to be a positive number, and it's not so obvious. It's not so obvious. But let's, for the moment, assume T0 is positive. And let's also introduce a name. Let's give a name to this temperature. Let's call it T1. Okay? So for temperatures smaller than T1, we can have more solutions. This is an important condition. T is smaller than T1. Okay, and that's T1. Now, that's condition number one, and then we can continue. We have succeeded in finding cases where the square root is a real number. And to continue, let me write this in a simplified way. This would be beta plus minus delta. Delta is defined like that, so the square root of delta square is delta. That's what we have here, 2 gamma. Okay. And this whole thing now also has to be positive, because here we have p squared. All right. And we have two possibilities, plus and minus, so let's go case by case. One case is very simple, right? Because minus beta is a positive number and gamma is a positive number. So if we add here plus delta, delta being a positive number, then that definitely is positive. So we have already our second type of solution, which the challenge of this exercise is to fit everything in one whiteboard, right? So let me remove this, which we can recover from that and that, and already write a second type of solution that corresponds to p squared equal minus beta plus delta over 2. Okay? So provided that the temperature is below T1, solution for T smaller than T1. Provided that the temperature is below this T1, it has emerged naturally from the combination of the parameters in the model, this solution always exists because this thing is positive. We don't know if it is a maximum or a minimum. And it exists at very low temperatures all the way down to 0. So that's interesting. Here we have a solution that dominates at high temperatures. Here we have a solution that in principle exists all the way down to 0, assuming T1 is positive, of course. All right. And now we have to worry about the other case. Let me remove the plus here. Let me stay only with the minus. So minus beta is positive, gamma is positive. So it's not obvious whether this is positive or negative, but we want it to be positive. How do we go about this? So essentially, since gamma is positive, we need minus beta minus delta to be positive. So we need minus beta to be bigger than delta. And this is going to be satisfied as long as beta square is bigger than delta square. Okay? So if this is satisfied, this is satisfied. Because beta is a negative number. So let's look at this one. This is very easy because delta square is actually beta square minus 4 times t minus t0. So these two I can remove by subtracting on both sides of the inequality. I can divide in both sides by this thing, and in the end I get 0 has to be larger than t0 minus t. I am using the minus sign, which means that the temperature has to be bigger than t0. What a convoluted situation, right? So we have a third solution, third category of solutions. Have to be careful because the first time we recorded this video, here live it was okay, but in the video the whiteboard was really unbearable. Okay, so the third category of solutions corresponds to p squared equals to minus beta minus delta over 2 gamma, and these guys exist for temperatures that are both below T1 and above T0. So we need the temperature to be below T1 and above T0. This is solution for this condition. Now, first thing to point out, this can happen because T1 is T0 plus something positive, so T1 is bigger than T0. No question. So we can have temperatures in between. In fact, this can happen even if T0 is negative. Don't care. Then it will happen for temperatures between T1 and 0. Of course, T1 has to be positive for this to make any sense. Very good. Let me erase now. I think I'm going to manage to make it in one single whiteboard. Okay, so what have we learned? We have different solutions in different ranges. This one always exists, and it is a minimum of the energy for temperature above T0. These two not always exist. They exist in these ranges, and we don't know if they are minima or maxima. We know that the energy has both. So which one is which? Which one is which? Well, it's not so difficult to actually figure out because, of course, in situations like at T star, we have a minimum at p equal to 0, and then what do we have? Minimum, maximum, minimum, right? So it's obvious that it will always be the case that the minima, the polar minima, the minima with a finite polarization, will correspond to polarization values that are bigger in magnitude than the maxima. So the maxima must be placed between p equal to 0 and finite p. So this p is always larger than this p, the p that we have there, right? And so by inspection here of these two quantities, we can figure out immediately which one is bigger, regardless of at which temperature we are. Here we have 2 gamma in the denominator in both cases, so that doesn't make them different. But here we have positive number plus positive number, so this probably is biggish. And here we have positive number minus positive number, so this one is going to be smaller. Okay, So minus beta plus delta is always bigger than minus beta or equal than, always bigger than or equal to minus beta minus delta. Okay, so this guy, solution number 2, has to correspond to the equilibrium point that has a bigger polarization in magnitude, and solution number 3 must correspond to the equilibrium points that have a finite polarization but smaller in magnitude. And of course, solution number 1 is here at 0. That's it. These are the minima, and these are the maxima. All right. So now, to completely figure out what's going on, let's plot the polarization as a function of temperature. Okay, and let's see what these equations are telling us about that. Okay, I'm going to do this here, but I'm going to make a bit room. Okay, solution number 2 is always minima, you have it there. Solution number 3 is always maxima, you have it there. Let me remove what I just wrote, so I can draw here with some space polarization versus temperature in our system. And let's stay with positive polarizations for the sake of simplicity. All right, let's imagine we start at high temperatures. We prepare the system in the paraelectric phase, right? We simply go to very high temperatures. We start here, and we cool down. We cool down. If we cool down, in principle, we stay in the paraelectric, in the state with P equal to 0, paraelectric for short. Okay, and maybe if we cool down very, very carefully, we can stay there down to very low temperatures, but there is a limit temperature beyond which we cannot be there. Why? Because the minimum stops being a minimum, and then that temperature is T0. Okay, so we can imagine that we cool down until we reach T0. So T0 is the temperature that sets the limit of stability of the paraelectric phase, of the high symmetry phase. This looks awfully ugly. Slightly better. Okay. What happens there? What happens at T0? Well, at T0, if this guy stops being a minimum, we are a little bit in the situation here in blue that I'm going to emphasize now. We are in this situation. And the system will evolve discontinuously towards the available minimum of the free energy. Of course, the system cannot disappear. It always has to be in the minimum of the free energy. So if all of a sudden, you used to be happy here, but all of a sudden, we remove, it's like removing a chair between, like being sitting and getting your chair taken away from you. You have to fall, you fall on the floor, and this is the floor of the system, right? So the system has to undergo a discontinuous transition to a different phase with finite polarization, and then we keep cooling down. That's what we get. This temperature dependence, by the way, of course, we could work it out from these expressions by plugging in what delta is, etc. All right. So cooling down, let's put in blue, we go down this way, then we have a phase transition, and down this way. Okay. It's probably going to be experimentally difficult to get to T0, but we know that we cannot get beyond T0, because beyond T0, we don't have any high symmetry minimum any longer. But now let's imagine we heat up. Let's imagine we prepare our system at a low temperature in a positive polarization state, and we heat it up. What's going to happen then? Okay, if we heat up slowly, carefully, so that we make sure that there is no reason for the system to abandon that minimum. So we will come over here. We will cross this T star that we have indicated before. I don't know exactly where that is. It has to be above T0, we said, so we cross above T0. And eventually, we will hit T1. This minimum cannot exist beyond T1. T1 marks the limit of stability of my ferroelectric minimum. So at T1, at a different temperature called T1, I have also a discontinuous. I have a phase transition that is also discontinuous. So this very simple theory is telling us that in this kind of material, or according to this theory, the transition temperature, the Curie point if you wish, changes depending on whether we cool down or we heat up. In general, it can change. The transition point cannot go to arbitrary values of temperature because there are limits. When we cool down, T0 sets the limit. At that temperature, we have to develop a polarization necessarily. And when we heat up, T1 sets the limit. At that temperature, we lose the polarization necessarily. All right. If we think about the situation at T1, this is a very interesting situation. T1, mathematically, is the temperature at which we go from a free energy that only has one feature, which is a minimum here at P equal to 0, to develop eventually multiple minima, right? And of course, when the new minima develop, also the intermediate maxima have to develop. So these things have to happen together. Okay. So if I draw the free energy at T1, let me draw it right there, although I'm not sure how that's going to work. Let me make a bit of room. If I draw the free energy at T1, it's going to look like this. Where these points here are inflection points, such that if I keep decreasing the energy, immediately I generate a minimum and a maximum. Okay. So below T1, I already have a minimum and a maximum. And above T1, I don't have any minimum, and therefore the system has to experience the phase transition. All right. Now, beautiful. This happens experimentally. This is hysteresis, of course. This is called thermal hysteresis. In reality, experimentally, probably we never reach the limit of stability, the limits of stability T0 and T1. So in reality, probably the phase transition when we cool down happens here, when we heat up happens there, or even they can happen very close by. If all this happens at very high temperature, for example, and we have enough thermal activation to escape from minima and to jump over barriers, a variety of things can happen, of course. But the basic phenomenology is here and it's quite nicely captured by this very simple theory. Final point is that, well, a couple of final points. Imagine that we have T0 negative. That would correspond to a system where in principle this state can survive down to 0 Kelvin. Okay, I'm not sure there are many experimental examples of that. Right now, none comes to mind in the field of ferroelectrics. But you see that getting there will be very difficult anyway, because even if we have this minimum, it will become shallower and shallower, and we'll have a very dominant minimum of low symmetry, right? So the system will eventually, most likely, jump. If it doesn't jump, we would not realize it's a ferroelectric. All right. Although we would not realize easily. Okay. And the second consideration is that our T star, from everything that we have drawn here, clearly has to be a temperature where we have this situation with 3 minima and 2 maxima. So about T star, we know that it has to be between T0 and T1, right? So tentatively, let me draw it here. Actually, T star was something that we introduced at the beginning as some sort of idealized temperature, but one was that we have a model. We could actually derive T star from the parameters of the model, because T star, by definition, is simply the temperature at which the free energy of the state with zero polarization at T star is equal to the free energy of the state with finite polarization. So the state number 2, let me call it P equal P2 at T star. Okay. So if you want to do it at home, you can pick up this expression for the free energy, make P equal to 0. That's the free energy at P star, which by definition is 0, by the way. By choice, this free energy is 0. But then you have to also plug in the expression for P squared corresponding to this minima. It's not very difficult. Solve them for the temperature. Evaluate at T star. That has to be 0. And therefore, you can, with that relationship, you can actually express T star as a function of alpha prime, gamma, beta. Okay? It's a bit of work. It's nice. It can be done. All right. So this is all I wanted to tell you. Simplest free energy model to explain a discontinuous phase transition, generally, in particular, in a ferroelectric with P, where P, the other parameter, is the polarization. Questions?